we looked at continuity last time. Right, we've been evaluating limits. Right. But all of the limits we've been evaluating have been approaching 8. We haven't actually been examining how the function behaves long term yet. That's what we're doing tonight. These are called limits at infinity. Right, so there's two broad types. You have the limit at infinity, x approaches infinity, and x approaching negative infinity. Right, so the right-hand behavior, the left-hand behavior. For another case, it's what is the function doing on the ends? Infinity is the right hand, right, the right end, and then infinity is the left end. We can now define horizontal asymptote as just simply whatever that limit is. So if the limit as x approaches infinity equals some value, or as x approaches negative infinity equals some value, y equals that value is your horizontal asymptote. And you can have more than one. You can have two horizontal asymptotes. Right, function can do two different things on either end. Also, unlike a vertical asymptote, function can cross its horizontal asymptote. And there's no limit to how many times it can cross it. Right, and then of course, you can have your function just blowing up on either side. Right, so you can have infinite limits at infinity as well. An easier way to look at limits at infinity is kind of, is the function stabilizing? Does it stabilize to some value? If it does, that's a limit at infinity. Right? You may also hear me say it converges to some value. It's the same thing. So actually evaluating limits at infinity. Unlike with previous limits where you can just plug in a value, infinity is not a value. You can't really just plug it in. What we do is plug it in. We kind of just look at it and go, okay, so what's happening? Infinity, so take an infinitely large number, square it. Still infinitely large, right? Multiplied by 3, it's still infinitely large. Infinitely large number times 5 is still infinitely large. And then plus 1. So kind of what we have in the numerator is infinity minus infinity plus 1. But infinity minus infinity is not necessarily 0. So a better way to look at it, 3x squared versus 5x. All right. Take a really large number. Say a trillion.
Yeah.
What's a trillion squared? It's 10 to the 18th. Times 3. So let's say that you have 3 times 10 to the 18th dollars in your bank account.
Right.
You spend 5 trillion. Does your bank account even notice? No. add 1. That 3x squared is dominating. By the way, the same argument is going to show that that x squared in the denominator is dominated. We should get 3 for this limit. We're now going to algebraically justify that. And it's using kind of the same argument. Look at the denominator. Factor out your dominating term. Factor out x squared, that's what you're left with. Take that 1 over x squared, apply it to each term in the numerator. We can use limit laws now. And then use that limit. Limit as x approaches plus or minus infinity of 1 over x to the n of 0. And that is very easy to justify. What happens to a fraction if the denominator begins to get larger?
Number, so it's 0.
The overall fraction gets smaller. Specifically, how's it getting smaller? It'll get 0. Never hits 0. It does approach it. Limit laws. Will allow us to treat all those terms just as 0.
Just because they have an x in it?
Over x.
Yeah.
Over x squared, right? Really what's happening is each of those terms, the denominator is going to keep getting larger and larger and larger while the numerator stays the same.
Well, yeah, that's right.
So all of them are going to go to 0. So with the limit laws, this is, oops, not great. Getting rid of those terms that go to 0, we're going to be left with just the limit of 3 over 1, which is a constant. That's 3. That is the algebraic justification. But again, intuitively, you should be able to see what the limit is. X approaches negative infinity, 5x cubed minus x over 2x to the 4th plus x. a quick look at this, you should see the limit 0. That x to the 4th term dominates and it's in the denominator. Right? Your denominator is growing quicker than your numerator, which means you're going to go to 0. Let's algebraically say it. Again, factor out your dominating term from the denominator. Apply that, and so divide each term in the numerator by what we just factored out. If you go ahead and look, using limit laws, we're going to know that all 3 of those terms will go to 0. So we're kind of just left with the limit of 0 to 0. Quick look, what should this limit be?
-2.
Now let's justify it. We're going to factor out an x cubed from the denominator, right? You'll be left with 1 minus 4x squared. So divide each term in the numerator by x cubed. Notice, using limit laws, we can just say those terms are going to go to 0. If you apply the limit laws just to those, you can be left with the limit as x approaches minus infinity of -2/1, which is just negative. Being able to take limits at infinity, you're going to do that a lot in Calc 2. We'll also actually do it again later this semester. We'll start looking at integrals. it will be 0. If you just do substitution, again, I use that very lightly. Square root of infinity minus infinity. Square root of an infinitely large number is still infinitely large. That's another indeterminate form. Infinity minus infinity is indeterminate. Believe it or not, there's actually different scales of infinity.
Does it matter if it's negative infinity or positive infinity?
Yeah. So if that was positive infinity, that would most likely just be infinite.
Because there's no denominator.
I'd still try to algebraically justify it, but I'm pretty sure it'd be infinite.
Yeah.
Because instead of getting infinity minus, you get infinity plus infinity in this case. So there's different scales of infinity, which is why you can't just say infinity minus infinity is 0. One of the most mind-boggling ways to see that, there's actually a video, Vsauce did a video on measuring infinity. If you look at set theory, cardinality of a set is the quote-unquote size of the set, how many elements it has. Natural numbers are infinitely countable. The integers are also infinitely countable. In fact, we call the cardinality of the natural numbers a left null. It is the smallest known infinity. And we say that something's countable if there's a one-to-one correspondence to the natural numbers, which there is between the integers and the natural numbers. You can easily assign each integer a natural number. So they have the same cardinality. The rationals are also countable. They have the same, it has the same cardinality. The reals are the first time where it's not countable. So it's an infinite cardinality. Complex numbers. Also uncountably infinite. It has a cardinality of infinity. But the complex numbers cardinality is actually larger than the cardinality of the reals. So different scales of infinity. Complex number of infinity is larger than the real number of infinity. And we can keep going. There's number systems beyond complex as well. Right here, I think I would have gotten doesn't matter, any of them. Infinity over infinity is indeterminate for the same reason. So the idea is find a function identical to that given function everywhere except quote unquote at negative infinity. Take a conjugate. And I want to do the same thing. Factor out an x squared from underneath the square root. We're going to split that square root into two. Right? Square root of x squared times the square root of 1 plus 4 over x. What's the square root of x squared? What is it?
X over 1. Absolute value.
It's the absolute value of x. Because x could be either positive or negative. When you square it, it becomes positive. I'm going to multiply both numerator and denominator by 1 over absolute value of x. How would that simplify? Well, x is approaching negative. Which means all the values of x are what? Negative. So what does the absolute value of x become? Well, I agree, if you plug in a negative into the absolute value, it's going to give you a positive. But how would you represent that? In other words, what is the definition of absolute value of x? about definition. Absolute value of x becomes negative x because x is less than 0. But then that 4 over x is just 0. We can treat this as the limit, negative 4 over root 1 plus 1. Square root of 1 plus 1 is what? Square root of 1 plus 1.
Oh,
2. Negative 4 divided by 2 is a constant. Limit's negative 2. In fact, the idea of infinity is actually a new concept, relatively speaking. If I remember my history correctly, I think it was first really examined in the 1900s. So just last century. Before then, they just kind of ignored it. 0, I believe, is also relatively new. I think 0 was really first thought about in the 1800s. So if you're a mathematician back then, and you even talked about the idea of infinity, they probably shanked you. No, we don't discuss that. And even the physicists at the time, I think, didn't really think of infinity so much. So they thought of the universe as finite. Really large, but finite. Then we start to think of the universe being infinite. And now there's two schools of thought. The universe is infinite, and the universe is actually finite. I'm in the finite school of thought. I don't think the universe is infinite. It is finite. But I also believe there's multiple universes. I'm the multiverse branch. We're just one of an infinite number. And so what about this one? Well, following following the same kind of thought process, just look at each term. Square root of 9x squared plus 1, as x approaches infinity, that's also approaching infinity, right? The negative 3x, though, approaches negative infinity. So that's kind of like infinity minus infinity, which is indeterminate. Oh, well, this is good news, though. You get 1 over square root of 9x squared plus 1 plus 3x. Well, if you just look at that denominator, the square root we already said is increasing without bound, right? What about 3x as x goes to infinity? Does that also increase without bound? So doesn't that overall denominator just keep increasing without bound? Which means limit 0. You can just use a basic change of variable. Let u be that entire function. Then u goes to infinity as x does. That just then becomes the limit of 1 over u as u goes to infinity, which is 0. So this limit's 0. I want to make a slight change. I want to make that goes to positive infinity instead of negative infinity. Because negative infinity is going to be the same argument, and it's boring. If we instead go to positive infinity, that square root is increasing. We already saw that, right? That 3x is increasing. That limit's infinite. So that limit's just infinity. There is no algebra that needs to be done that is not indeterminate. Again, if it was the original negative infinity, it's the exact same argument, except your denominator would be minus 3x instead of plus 3x. But your u would still go to infinity. X approaches negative infinity. Natural log of negative x over x. Again, something else you're going to have to get used to. The domain of log is positive numbers, right? Log of negative x is defined. It means your x's have to be negative. So the domain would be negative infinity to 0 for this. Right? You can't just go, oh, log of negative x, therefore it doesn't exist. It does. You just adjust your domain. And notice what our limit, what our x is approaching. It's approaching negative infinity. So this limit could exist. If that x was approaching infinity instead, the limit doesn't exist. Because then you'd be taking natural log of negative numbers, which does not exist. Okay, algebraic justification here is going to be a little difficult. I'm going to use logic. First thing I'm going to do, though, is a change of variable. I'm going to say u is negative x, so u would go to infinity as x goes to negative infinity. It's not x. This is the one I'm looking at. Log u over u. And then whatever that limit happens to be, we're going to multiply by minus 1. Well, think of it. Natural log of u if we let u keep going, log is growing, right? But the question is, how quickly does it grow? Actually, this shouldn't be in here for those justifications. Catch that. Actually, L'Hopital's really do this. That's okay, because I can justify it. I can justify it using pure logic. Grows very, very, very slowly, in fact. In fact, just for natural log of u to equal 10, you would have to be e to the 10th power, which is larger than 2 to the 10th. And 2 to the 10th is what, 1024? 5th is 32, 6th is 64, 7 is 128, 8, 256, 9, 5, 12, 10 is 1024. Shit, that's not good. I need a vacation. I know what 2 to the 10th is off the top of my head. That's really not good. That's a pretty large number. So you have 10 over 1024. Something larger than 1024. Okay. If natural log of u I want to be 20, that'd be e to the 20th, which is larger than 2 to the 20th. That's 1024 squared, which is greater than a million. You now have 20 over something larger than a million. Oh, okay. Well, e to the 30th. You get 30 over something that is larger than 1024 cubed. That's larger than a billion. Now you have 30 over something much larger than a billion. See the pattern? Let's go into 0. Well, they are both technically increasing without bound. The natural log is doing so at a much slower rate than u, which ultimately means your denominator is the dominating term here. What we would do is I would write natural log of u is much smaller than u for u being much larger than 0.
Is that what that means?
Yeah. So when you use the doubles, it usually means much. So for very, very large u, you have natural log of u being a lot smaller than u. Right, so that's my justification. It's not even 4:30 yet. This is my last example. That's okay, maybe I can give you time to work on group assignments. That's what was the worksheet. Limit as x approaches negative infinity, x times sine of 1 over x. Let u be 1 over x. What does 1 over x do as x goes to minus infinity?
Go to 0. Doesn't go to 0.
It's approaching 0. Now, I do technically need to be a little bit more precise. Here it didn't matter. Here we need to be just a little bit more precise. It's approaching 0. On the left. And all your values are less than 0. Right, because you're approaching minus infinity. Doesn't that limit just become limit as u approaches 0 from the left, sine u over u? What's that limit? I gave you that limit on Tuesday, last Tuesday. What was that limit?
Oh, it goes to 1.
If the limit exists, doesn't that mean the two one-sided limits are identical? Which means that limit's 1. Let's actually look at that graph, though. Because all the other functions we've looked at were not oscillating. Sine of 1 over x does oscillate. I don't think this is one I'm going to save either. I'll just use Wolfram to plot it. Oh, oops. I want that. This is the one I want. We'll show this. So that is from 0 to, or negative 2 pi to 2 pi. What happens is I expand this out. Okay, so that's pretty clear. Let me shrink it. What you notice is, yes, it does oscillate, but all the oscillations occurs in the center. It begins to stable out. In fact, the oscillations stop even before x hits 1. My plot range actually. Kind of see how it's oscillating too as you approach 0. Oh, and by the way, that limit as x approaches 0 is 0. That can be proved using squeeze theorem. Oh, good. Again, the working at infinity is difficult until you get used to it. It's, again, a different way of thinking because it's now going to be more abstract than concrete. Right? So are there any questions on limits at infinity?
I have a question on why you use the U.
I just did a change of variable.
Yeah, alright.
I just chose U.
Just making sure.
U is typically the go-to variable when you do a change of variable in Calc 1.
Oh.
I could have done theta.
I don't like that as much.
Could have done Y. I just can't really use X because I'm already using X.
Yeah.
But at advanced levels, I would have just kept it as X. Just rewritten it.
Yeah. Oh. it changes from limit to x going to negative infinity of x sine of 1 over x, how does that like change to the next one, to the limit of u going to?
So do you understand the previous step?
Well, I don't understand that stuff. What do you mean?
The actual change itself.
The change to u?
Yeah, so this here.
Yeah, like you're changing u to 1 over x.
All right, so you understand that, and you understand why it's approaching 0 from the left.
Because it's negative.
Good. So that's just a change of variable. So these two limits are exactly the same. Right? So x approaching negative infinity becomes u approaches 0 from the left. 1 over x becomes u, which means x has to be 1 over u. Does that make sense? Yeah. Just simple. Essentially, at that point, it's just a plug and chug. So good news and bad news. The good news is you only have one homework assignment. Web assignment. I'm not giving an assignment on 2.5 because that is the formal definition of limit. It's all proofs. It's kind of difficult to do that on web assignment. So I just don't do it. Bad news.
What? What do you?
Give an AI assignment and a test. AI assignment's not bad. It's just a bunch of limits, I believe. I don't remember exactly how many. Eight limits. For all 8 of those, you're going to do the same thing. You're going to plug the limit into AI, have it evaluate it. You would then evaluate it yourself, show them work. So this isn't like the project where you have to do tables. No, this is just you can use algebra. And then compare. Did the AI get it right? And if they're not the same, it's asking you to say who's right, which means I expect everyone to say that I'm right, not AI. And then I'll go back and apply to now AI is right. And why? So if AI did make a mistake, why? What mistake do you think it made? Why did it make it? Or if you actually are honest enough to go that you were wrong when you actually were wrong, what mistake did you make? Now, all of this has to be typed up. Even the limit evaluation. I'm not accepting handwritten work. So you are going to have to use something that has math typesetting. Microsoft Word has a built-in equation editor. Google Docs has a built-in equation editor. They're not the greatest, but they're sufficient. If you're really bold, LaTeX is your best bet. LaTeX gives you the cleanest. But you got to be really bold for that, because that's a coding language. Yeah, it's not a word processor. It's a language. What do you use? I use LaTeX. But I didn't start using LaTeX until I already got comfortable with another coding language. So at that point, I was already comfortable with coding languages, so it made learning LaTeX a lot easier. First time looking at LaTeX. It's one of those things of what the hell is all this? I can show you. Oh, no, I can't. I don't have it on here with. Actually, yes, I do. So let's go ahead and load up these examples. Right, so just to give you an idea, these are the examples with the PD already formatted as a PDF document. That's what it looks like when it's compiled. That's LaTeX code.
What if you tell GPT to put it in this code?
Oh, that's great.
Does that work?
In fact, that's how I learned it.
Okay.
Was mostly just using GPT to figure out how to do things. But if you have zero idea of any coding languages and something doesn't compile right, and you have no idea why, good luck fixing it.
You said you can't handwrite it.
I mean, you can, but not as your final submission.
Yeah.
So if you want to hand write it out first,
Okay.
be my guess. In fact, I would recommend you do that, and then do your polished type up from that.
What would you say is on the unit 1 test?
I'll get there.
Okay.
So I would recommend probably just use something like Word. And just use the built-in equation editor. It's easier. Right, make sure you read the instructions and you follow it. And then just like with the group assignment, there is the grading rubric there for you to look at as well, how it's going to be graded. After the test. So I did provide a review, except why are you not first? Now you're first. So review sheet along with its solutions. I would recommend you look over that review sheet. So it's going to give you a really good idea of what's on the test. I had the review sheet generated from the test. I wrote the test first. And then I had a review sheet written from that test. I just plugged the test into GPT and said, make a review sheet based on this test, but make sure none of the problems are identical. And that's what it spit out.
What is the AI assuming do?
I'll get there.
Okay.
I did put those two charts in here as well. You're going to be allowed to have those open and use them. Of course, you can also use your notes in your textbook for this take home. I can tell you the test is 6 questions. Obviously, read the instructions for opening the test. Once the test is open, the time limit starts and you cannot stop it. It is a 90-minute time limit, which is way more than enough time. I figure 10 minutes per problem and give you enough cushion time for uploading. Because you have to upload for each question.
Like the word?
Yeah.
And that we can read.
That will be, yeah, you can handwrite that. You'll just take a picture and upload to a single PDF file.
No JPEG?
For each question. JPEGs can have issues.
Okay.
I would recommend PDF. I've never had a problem with PDF, but I have had problems with JPEGs. Where even sometimes the image itself is broken and it won't download. Remember, each question needs to be its own upload, and that upload needs to contain only the work for that question. But that's all in the instructions. It covers only limits, excluding section 2.5. I'm not going to have you do proofs on the test. The proofs is just to see what a limit really is. I'm not going to test you on it. So you could theoretically take it now, because I've covered everything that's on the test. And so it's what, 2.2, 2.3, 2.4, and 4.6. AI will be due next Tuesday before class. The test is due next Thursday.
And when does the test open?
It's open now.
So, correct me if I'm wrong. The test is not proctored, like it's online?
Yep, it's not proctored.
Oh.
I don't do online proctoring. I don't like it. It's awful. It flags you for every little thing and then it makes me sit there and watch the whole damn video. I actually one semester had it flag someone was in the room. It was a goddamn poster on the wall. So it flagged every frickin' second as there's someone in the room. It was just a poster. No, thank you. So no, I don't do proctor. That's what the exams are for. It should go without saying the test cannot be worked on together. Also, the AI assignment, while you can work on it together to kind of figure out, okay, how you doing the AI prompts and all that, you do have to submit your own work. Right, so you're going to be required to submit the entire chat log. That obviously has to be your own chat log. Don't forget the 2.4 homework is due Thursday. This homework won't be due until next Tuesday. So next Tuesday is going to be busy. You have 3 assignments due. I was going to make the test due on the 23rd. I'm like, that'd be nice. I won't make it due on the same day as a project and another assignment. So you have more than a week to work on it. Like I said, you could actually theoretically take it right now. Everything that's on the test I've already covered. Any questions? Awesome. So I do have up here a sheet for you to fill out. If you didn't receive any of the handouts or a handout from the first meeting, just put your name here and check off which ones you need. I'll print them out and have them next time. So make sure you do that before you leave. For the rest of today, go ahead, work on the group worksheet. You're going to have quite a bit of time to work on it. So if you also want to work on that project, get the finishing touches, this would be a great time for you to do that. So think of this as just group time. Get in your groups so I can hand out the worksheets.